Welcome to lecture number 5, a lecture on making of decisions. That is, for the microcontroller to make decisions. Sometimes we don't, or very often, we don't want our program just to continue all forever, just going around doing the same thing. Sometimes, depending on what value the variables have or so forth, we want to allow the microcontroller to make decisions and do different things accordingly. So let's start off by looking at our just reviewing what we learned about variables. And so go to open BrightSparks 07 variables. 07 variables. And this is just to illustrate how we use variables. Just to start off on this lecture and couple it to our previous lectures. So we are kind of used to this stuff up here by now. Define on is high, define off is low, and define the pin that I want to be using as pin number 13. You're used to that by now. Now, what I want to do is, I want to make my little LED flash on the board, for instance. I want it to flash very fast to start off with, and then increase in the length of each flash, bit by bit, until it's taking very long between each flash. That's just for some other reason what I want to do. So what do I do to do that? Well, first we define a variable, and when in doubt, use int. So I'm going to define a variable called length time. In other words, that's going to be the length of the time of each of the flashes. Okay? And then I go into my setup and I say, right, let's make my pin be an output. We know that by now. Excuse me. And then I want length time to start off at 1. I could have it start off any value I want, but let's start it off at 1. Then we go into our loop, and you know this by now. Right to the pin, my pin, switch the LED on. Delay for length time. Right to the my pin off, delay length time. But now, instead of just going round and round the loop at using that delay, the delay of length time, which at the moment is 1, so it's going to be extremely fast. It's going to be, if we connected it to a speaker, it would be playing a sound of 1 kilohertz, in other words, round about there. So this is what it's doing at the moment, but what I do is now, let's make length time slightly longer. Okay? So at the end of the loop, we'd say my new length time is equal to my old length time plus 1. Okay? So this, of course, is not a mathematical statement. I can't say the length time equals length time plus 1. This is a computer statement, right? And the computer statement says, let this on the left-hand side be what I've written on the right-hand side. Okay? So I could have said, let t equal 10, and that will make t, take the value of 10 and put that in our variable t. Remember, our variables are just memories, like calculator memories. They're just a lot of them, and each of them has a name. Right, so I say let my calculator memory, length time equals the old length time plus 1. Okay? And then I go back up to the top again. So let's try this out. So just make sure that you've loaded this guy, 07 variables. Remember, load BrightSparks 07 variables. Okay. And for this to be correct, if I remember correctly, this is where our previous list of examples has changed. So I trust you have done your homework and have loaded the new list of BrightSpark programs into your computer. Right, so we are now on 07 variables. Okay, and I've defined those, and I run that, and I try it out. So you've noticed by now that we don't have to put the test 1 through first. We can just compile and run straight away. So we don't have to use this one that checks to see that everything's a honky-dory. We can just push that one and it compiles it and stores it on the Nano. So make sure your Nano is connected to your USB-C, connected to your computer, and click upload. Right, so it compiles it and uploads it. And you will see on your Nano what's happening. The little red light will start with very quick flashes and then become slower and slower and slower and slower. And that's because we're making our length time, which is the length of time that we delay. We are making that longer every time we run round the loop. Every time we do that, we make length time 1 longer, 1 millisecond, 1,000th of a second longer. Okay, now there are a couple of things that we can do differently now that we've learnt about them. So let's give them a bash. Okay, I said if we wanted to increase the length time by 1, we could just as well have increased it by 10. Okay, and that will make the speeding up of the slowing down of the flashes faster. In other words, it'll slow down more quickly because each time we're making length time 10 bigger instead of just 1 bigger. So give it a bash, upload it, and you see we start off already with a slower flash rate, and we get to a very slow flash rate quite quickly. Okay, let's try another thing that you've learned about, or that I've told you about, and we're learning more about it now. That's how we said previously. We want length time equal to old length time, new length time equals old length time plus 1. Right, we learned about another guy, plus plus. And instead of length time equals old length time plus 1, we have a command that just says increment length time. Okay, increment it. So make it 1 more. And that then will be exactly the same as our previous little program that we ran that actually made the times increment just by 1. So we just try loading that up to our microcontroller, and you will see flash, 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 etc. Right? So we've done the same as we did just now. Let's try something else. Then we did a length time equals length time plus 10. Now that doesn't work with this guy here, right? This guy only increments by 1. We've got no choice other than that, right? But we do have another guy that we can use, another shortcut, and I've mentioned it, but you haven't used it yet. So let's do it. Length time plus equals 10. Okay, so now that means length time equals the old length time incremented by 10. Okay, so that's like our memory plus button. If we have 10 sitting on the screen on our calculator and we push memory plus, then it takes 10 and it adds to whatever length time is, or memory is on our calculator. So you see, this guy will do the same as our second program that we tried out. Let's just upload it and make sure it's doing what it should be. Okay, so now you see the flash is getting longer, but they're getting longer lots faster because we are adding 10 each time to length time. Okay, so we have in our arsenal now, we have more than one bullet, and let's just review them. If we want to add just one, we can just use increment. Okay. If we want to add just one, we can length time plus 1, right? Okay, a little bit interesting there. Oh, let's compile that just for fun. Let's compile the error. Okay, so I'm just going to check. You saw, of course, what mistake I made, which is very typical. Let's see what it says. Okay. We open that up slightly. We see, oh, here's a problem, right? Length time equals time plus 1. Okay, that's my problem, says the compiler, and it says time was not declared in this scope. Okay, immediately you see, hang on, probably I meant length time. It's even guessing what you think. It thinks you should have meant, and I've spelt it incorrectly. Right, so I go down again, fix it up. And incidentally, do you see that highlight? That is highlighting where the error happened. It's good, eh? So it says that's where the error is, and I'm giving you a tip as to what I think the error is and what you're going to do about it. Well, what we're going to do about it, we are going to fix it. Right? Try compiling again. Everything's honky-dory. Upload it. Everything's fine. Okay? So that was to make length time 1 longer instead of just length time plus plus. And then we had length time equals length time plus 10. Just for fun, let's make it 100 this time. Length time equals length time plus 100. And we can do that. Let's upload it just for fun. And you'll see it immediately start relatively slowly and very quickly start making very long flashes. And we said a shortcut for that is length time plus equals 100. And if we compile that, we see exactly the same. It's flashing slowly and getting slower all the time. Right, interesting how we have a couple of ways of doing the same thing. And this is a lesson in programming. Beginners often come to me and to all other people who program and say, how do I do the following? And we answer, which of the 100 ways would you like to do it? So there are often many, many ways of doing exactly the same thing, and it's up to the programmer to choose which one he likes today. or which one is faster, or which one looks more logical on the screen for when I read it later on. And doing that, we can have our code optimal for optimal reading in the future. Choose the one that looks most logical to you. Sometimes choose the shortest one, but choose the one that makes sense to you now, because it'll make sense to you later, because you're always going to read your code later on and not have a clue what you did. You warned. Okay, fine. So now we've finished playing with our variables 8.4. Okay, now the for command is very powerful. It's very powerful, but because it is powerful, you need to keep your wits about you, but I'm sure that you'll see how easily it can be used. The for statement comes before the beginning of a block. Okay, so there's a for, and there's the beginning of the block, and there's the end of a block. Okay, so here's the for statement. There's the beginning of a block, there's the end of the block. So in here, we're going to do something, right? And we're going to do it over and over and over again. Okay? But this is not like our loop function that just carried on doing that as into eternity. This will only go as long as you tell it to go. So, to start off with, there are 3 commands or statements inside a for block. The first statement is the one that you use to start things off the way you want to start them, right? So I want to start off with our variable named I, okay? And I want I to be 1. That's where I want to start, okay? Fine. So it will start with a variable called I. The second statement here is the one that is run before we run the block each time. Remember, we're going round and round and round the block, and this one we have to do before we do it, before we do each time we go round the block, including round the block the first time. Okay, so in our example here, the variable I must be less than 10. Okay, if the variable I is less than 10, then go round this block. Okay, go one time through the block. Okay, and then this statement, the third one, remember they're always 3, and like all of our statements, they end with semicolon, except the last one, but that's trivial. So the third statement says at the end of the block, in other words, when we reach that last brace, what must we do? We must do this. Make I equal the old I plus 1. Okay? So the old I, the first time round, was 1. When we reached the end of the block, we said the old I plus 1 becomes the new I. So now I is 2. Now we test before the block, and we say, is I less than 10? Yes. So, because it's 2. So, do the block once more. Okay, so we do another one time through the block, whatever we've told it to do over here. We go through, and at the end of the block we say, new I is old I plus 1. Old I is 2. I plus 1 is 3. So the new I is 3. Right, so we go to the top of the block again. Before we run it again, we check, is I less than 10? Yes, it's 3. So do the block again, and you've got the idea by now, right? So when I happens to be 9, okay, so we've just come through here, and I is 9, and we say I new I equals 9 plus 1, right? Now I is 10. So we now check before we do the block, okay? Remember, I is 10. When we reached here, it was 9. We've made it 9 plus 1, 10. Is I less than 10? It's not less than 10. It's equal to 10. And that doesn't say less than or equal to. It just says, is it less than 10? The answer is no, it's not less than 10. Okay, then you've finished with the number of times you went through the block. Carry on with the next command. Okay? So that's how the for loop works. And so I can just mention to you that before we go and actually try it out, that we are allowed to do the following. If, for instance, we haven't used a for up before this, pun not intended. If we don't have an I before this, right, we know that we need to initialize. It has to know about I before it can use it. And so we're allowed to just say, I have an integer called I, which I'm now going to use inside of this block. Okay? So I've declared it at the same time that I made it equal to 1. And so that is the same as that, but we do that when we don't have an I elsewhere in the program that we want to use. And then secondly, remember when we talked about scope, we said a variable is only understood or remembered or defined inside the block. And so we will only know about I inside this block. Why? Because we defined it as part of this block, right? So I will only know what's going on in here with the I. The minute we finished with I, the program won't know about this I anymore. So that's just in passing. We'll do that, and we'll do it here inside of our program. So let's go to our program. We've loaded 084. Load 084. And we load it into our IDE. And there it is. Okay, fine. So now, this is what we recognize already. We know that define that is high, low, mypin 13, all of this is very familiar already. Fine. Now, I want to use the variable I, and that's used there. Used there, apologies. So before I use it, I must initialize it. Okay? So I've initialized it, and when in doubt, use int if it's a number, right? So before we start, I is 1. Okay? Now, is I less than 10? Yes, it's 1. So switch on my LED, delay for 1 times 100, in other words 100. Digital write, switch off the LED, delay 1 times 100, which is 100. Okay? Now we've reached the end of the for block. So what must we do at the end of the for block? I equals old I plus 1. I is now 2. Right? Old I is 1 plus 1, 2. So I is now 2. Right? So we finished the end of the block. We now come to the beginning again, and we test at the beginning. Is I less than 10? Yes, it's less than 10. So do the block. Now we're going to delay 200. 200. I equals I plus 1. I becomes 3. Is 3 less than 10? Yes. Delay 3 times 100. Delay 3 times 100. And so off. All the way until we reach 9. And when we say what do we do at the end of the block where I is 9? And we say I is 9 plus 1, so I is now 10. Go to the beginning of the block, check at the beginning of the block, and it says, is 10 less than 10? No. Boom, and we finished. Okay, and we are now going to go back to the loop and run it again. So this is going to happen all the time because that's the loop, but we're only going to go from 1 to 10 in steps of 100 in our flashing. Right, so let's try uploading it. And you'll see on your LED, it's flashing longer and longer and longer. And then it starts quick, quick, quick again. Why? Because it's finished the 10 of them. And it will go back and start with 1 times 100, 1 times 100, 2 times 100, 2 times 100, and so forth. And that's how we're going to continue going through our for loop. And I said in passing, and you will see now why it makes sense. Sometimes I've just initialized I, and this is the only place that I want to use it, so I'm allowed to do that. Okay, and so I've now initialized the variable called I, and I've set it equal to 1, and it's now running around the for loop. Okay, just to make double sure, we upload that, and it's all fine. It will do exactly the same thing because that int has defined that I. If we leave out the int, okay, I like showing you errors so that you recognize them when they happen with you. Okay, so we haven't defined I, so we tried and compile it. I was not declared in the scope. Right, so we declare I, and we tried again, and it's fine. Okay. Right, that is now our for loop. Now we want to learn some other things. So let's open BrightSparks 09. Okay, and 09, we start with a completely different concept. The concept of a serial port. So let's go back to our PowerPoint presentation, and we talk about talking back and forth between the Arduino and the computer, or the Arduino and another Arduino, or the Arduino and some other sensor, etc., etc. A lot of the work that a microcontroller does is to talk with other bits and pieces. And I need a little bit of medicine for my throat. Right, so our USB connector to our computer is just an example of how microcontrollers talk. And if you were to open it up, there are basically just 4 wires. The 4 wires, the new USB-C has a couple more, but don't worry about that. Basically, USB consists of just 4 wires. Now, how do we use those 4 wires? Well, there has to be a power wire because somehow our Nano has power to it. So there's a power wire, and there's a ground wire, a 0 volts wire, define where the 5 is measured from. And then there are just 2 wires for data. Too much. The bottom line is that all communication has to be serial. It has to be changed from some other thing that we want to send to some other number in binary, and then that gets sent along the wire. Okay, so for instance, the letter A in binary is 01000001. Right, so if we want to send an A to our nano, or we want to send an A from our nano, then we must send along the wire a low, in other words, 0 volts, and then it must go high for a period of time, low, 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 high. Okay, right, so there's a voltage going up and down between these 2 wires, and that voltage is 0.5000005. Okay, that's what we need to do to be able to send the letter A. Okay, so similarly, when we receive a letter from the Arduino, the computer will see some voltages: low, high, low, 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 high. Okay, and when it's seen those voltages, it then converts it to binary. It says, okay, all those lows and highs must mean that we have a binary number 01000001, which it looks up in its table and says, okay, that's an A. So from one side to the other side, we have sent the letter A. Okay, and so to summarize, we take some other letter or some other value that we want to send. We convert that to a byte, and that's called a byte, 8 bits. And we then take that byte and strip it down to just single bits, 8 of them. And we send those 8 bits along the wire. And then on the other side, we receive those and take those 8 bits and convert it, plus stick them all together into one byte, and then that byte the computer then knows represents a letter or a number or whatever. All of our communication is via serial. Almost all. But all that you will bump into at the moment. Right, so let's have a look at how we do that inside the Arduino, or the Arduino program. Okay, so we load 09 BrightSparks 09 serial. Okay, and there's our serial example program. Okay, so now I start off and I say I have an integer I, right, and I'm going to use it. But before I use it, I now want to start my serial. Now let's try that again. Okay, so there is our, oh man. Okay, there we have our program, 09 serial. Right, so we, as you know by now, we first run setup before we start anything else. And what do we do in setup? In setup, we set up our serial connection. In other words, we tell the computer, the microcontroller and the computer, that we are now going to use a serial connection. And it might have been obvious to you, but it might not while I was talking. Somehow the computer must know how often these values change, right? Because a low and a low and a low and a low and a low following each other means that somehow we must know how long each bit is, okay? And so the first thing that we do is we tell our Arduino, look, we are going to talk at 9,600 bits per second, okay? So those bits are going to come by at 9,600 of them per second, okay? And that means that the computer and the Arduino now know how fast these bits are going to be rushing by and how fast it must catch them. So 9,600. Now the number there is historical. It comes from many years ago, and so typically standard bit rates. One of the standard bit rates is 9,600, and it's kind of the one that usually comes up when you switch on a machine. It usually wakes up in 9,600. If not, it wakes up in 115,200, but don't worry. This is often, or most often, the speed that it wakes up at. So I'm choosing that, but I can choose other speeds. We're going to talk over a serial connection at 9,600 bits per second. And it's also referred to as, bits per second is referred to as baud, 9,600 baud, B-A-U-D. But that's archaic. It's usually just bits per second. Right, now we define an integer, I, okay? When in doubt, define I. So we define I and we say, fine, I would like you to print I to my serial connection, okay? So one of the things that serial knows how to do, it knows how to begin, and it also knows how to print. So to my serial port that I've started up there, print the number I, okay? So it'll print whatever the number I is, okay? However, we haven't told it yet what the number I should be. So I must start off this guy and say, I want I to start off with as being 1. Okay? And that's also a nice way of declaring that integer. All in one fell swoop. We've declared I and we've said start off with it being 1. Okay, so it's going to print 1. Then it's going to print a space. Now this is the first time that we are bumping into a string, and this is specifically a character string, a 1-character string, and it's just plain and simple a space. So there are 2 single quotes, and between the 2 single quotes is the single character space. We could, of course, have put another character in there, and we'll do that in a moment. Fine. Now we're going to delay a little bit. The only reason for that is these numbers rush by at such a speed that you won't be able to see what's happening. So I'm going to delay a tenth of a second in between the numbers. And then I make I, new I equals old I plus 1. So now I is going to be 2, and it's going to print 2, and so forth and so on. Right. So I can now compile that, and it's all compiling fine. And I can upload it. And it's uploaded fine. Okay, so if you now look at your Arduino Nano, you'll see one little light next to our power light. You'll see the light on the other side of the power light from the LED light is going flash, 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 flash. That is the numbers going to the computer. The Nano is busy sending numbers to the computer, each one bigger than the previous one. Okay? Now, we do have a method. Right. If you now go to the extreme right-hand corner of your IDE, you'll see a little magnifying glass, and when you hover over it, you see serial monitor. Right. So if you now click on that, then you'll see a window opens up with numbers scrolling by. And that's exactly what we have now been printing with our serial print. That is what the computer is receiving from the Arduino. Okay? So now you'll notice that if we push on the little reset button in the middle of your Arduino Nano, if you push on that, you notice we start at 1 again. Okay? Why? Because we've reset our Nano so that it starts the program all over again. And of course, we are starting our program starts with 1. Okay? Now, we might want to actually have these numbers all underneath each other. Right? So to do that, we go and we change this command to print ln. It stands for print line. Okay? So if we do that and upload it and have a look at our serial monitor, there we see the numbers going by, and we've added a line to a new line to each number. So I could have actually done that. Whoops, not that. That. Okay, now we no longer need that space between two numbers because we've got a new line between two numbers, and we can print them like that. We upload and look at our serial monitor, and there they go. Right? Now, you'll notice when I click on the serial monitor, you see some values, and then it starts with 0. What's happening is, if you look at your Arduino Nano, and you'll see an LED, not our blinking LED, but on the other side of the power LED, you'll see a little blinking red light. That is the Arduino sending the numbers through to the computer. That's what you see on your serial monitor. However, if we switch off the serial monitor, you'll see that those numbers are still flashing, that little LED is still flashing, which means we are still sending the numbers through to the computer. And so if we open up the serial monitor, we'll see we were already at 381. It had just been sending it. The fact that we look at it by means of the monitor doesn't mean to say that it's not sending information. And secondly, if we now click this, you'll see we got to 150, but then we start at 1 again. Okay, that's because each time we start the serial monitor, it starts the program over again. It resets the nano so that you can see the program happening from the very beginning. So remember that whenever you start the serial monitor, it'll rerun your program from the start. Just as if you'd pushed the reset button, which I'm going to push now, and it reruns the program from the start. Okay. Okay. So now, what about implementing our for loop in this situation? So I'm going to say for we start off with 1, for instance, and we say I want all of the i's up to 100, and at the end of the loop I want to just increment I by 1. What about doing it that way? Right, so we now have a for loop. We will print I and a line feed and then delay, just so that we can see this going by. And now we don't need that anymore because we are doing it up top there. So we close that, close our block, and now we'll get all the words or all the values up to 100, and then it'll start over again. Let's try it. Upload. My apologies. Upload. And we look at it. And we start with 1 again. Right? So we've used now our for loop in our printing of our in our serial monitor. Fine, and then I can do one more change if I want to. I can say, instead of defining I up there, let's just define it inside the for loop. Okay, that's a little bit cleaner and shorter. Let's try uploading. And everything's fine. And there we go, up to 100. And actually up to 99. Why? Because we have I must be less than 100. Okay, so you'll see as it goes by, 99 and then 1. Okay, if we want to include 100, and we say less than or equal to 100, upload, upload. Have a look at our serial monitor. Up to 100. See, now we include 100. Fine. Now, what about if we are printing a floating point number, or in other words, a float, right? Let's have a look at that. We load up BrightSparks serial format. Okay, so look at that. We are there doing the same thing as we were doing previously, except that we are now dividing by this fancy decimal number, right? So our answer is not just going to be 0, 1, 2, 3. When we print, we're going to be printing a number that is a decimal number. And so I can upload that. And try it out. And there you see from 0 to 1,000, taking that number and dividing it by 3.14159. And that's the answer. But here we've been using many more decimal points. We are actually more accurate than the answer reflects. So we have a way of sorting that out as well. We can say, comma, 5 decimal places. Okay, upload. Have a look at the answer. There we are, up to 5 decimal places. Okay. Now, long time ago I said the variable that we called a float, the type of variable which we called a float, was able to handle reasonably accurate numbers, but not very accurate numbers. And we can kind of see now, we have the ability to see that situation. Let's ask for 20 decimal places. Okay, upload. Okay, so that's up to 20 decimal places. Okay, however, if we go to 40 decimal places, upload, you see what's happening here at the end? Our float variable is only able to handle up to that number of decimal places. After that, it is not calculating the answer, and therefore it just prints zeros. So here we have an illustration of the fact that our Arduino can only calculate up to that number of decimal places, which is ample. Don't worry, that's a lot of decimal places, but it cannot calculate up to an infinite or a very long number of decimal places. Some of our other microcontrollers, which we will learn about in a while, in a month or so, are able to calculate even more accurately. Right, so that then gives us the method of having as many decimal places as we like. And there I've changed it to 6. And there's our answer. Okay? Right. Right, we now go back and have a look at our next flow control command, and that is if. So let's just look at that. If we want to check for some condition, then we can use the if statement, and that will allow the microcontroller to do stuff or not do stuff depending on the answer of our condition. So I can say if some other condition, I is less than 10 or whatever you. Close the brackets, open the braces, and this is all the stuff that it will do inside that block, that if block. Right, let's look at an example. We go to open BrightSparks if. Okay, so we're going to do something like we did last time, and we will switch that on. And you'll see, you recognize this. There's our serial setup or initialization or begin, knows how to begin the serial transfer, switch on the serial transfer, you might say. And then we're going to use this for loop for int I equals 0 to just below 10. And at the end of the block, we're just going to increment the I. Right. Now we're going to say if I is equal to, and note that is the equal to sign. It's a check, it's a test. It's not I equals 0. It's I is I equal to 5. If I is equal to 5, then print for me high. Okay? And then print with a line feed, I, and then delay a little bit, just so that I don't rush by too fast. Okay, so we're going to upload that. All uploaded fine. Let's look at the output. Right, so whenever I is 5, it prints that extra little high in there, and otherwise it just prints the number. Okay, so just a little tip here. If you want to stop this going by and freeze it, just switch off auto scroll. It carries on printing. You can see the position is moving here on that scroll bar, but we've frozen it so that we can see what's going on here, and then we can unscroll it, auto scroll, and it'll just carry on from the end. Just keep on scrolling as the data comes in. Fine. So now, what about something else? What about if we, instead of just having when I is 5, print I, otherwise just keep on going, what about looking at if, then, else? So we go to BrightSparks, if, else, right? So we can now say if I is equal to 5, then print I, else, in other words, if I is not equal to 5, then print this. And then when you finish doing that, just print the number as well. Okay? And delay a little bit so they don't rush by. So we upload that to the microcontroller, have a look at what the result is, and it's what we expect, right? Low, 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 low. Why? Because I is not 5. And when we reach 5, we print high. Otherwise, we print low, 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 and so forth, right? And in each case, so these lows and highs are printed from that block in the if-else block, and then these numbers are just printed after we printed either high or low. Right, and then there's one further option that we can look at. So we load if 0 or 10b, okay, 10b, And now we go, if I is 5, then print high. Else, if I is 2, print terrible. All the other cases, print low. And then print what I is and finish off. Okay, so we upload to our microcontroller and we have a look to see what it's doing, and that's exactly as we expected. Okay, 0, 1 are low because they're not the 2 or the 5, right? 1, it's not the 2 or the 5, so we just print low. These are the else, else, else. Okay, else, print low. If we 2, then print terrible. If we 5, then print high. Otherwise, print lows. And just to recap, right? If we 5, print high. If we 2, print terrible. Otherwise, print low. And when you finish doing one of those 3, and note, only one of those 3 will happen, then you can print the number itself and delay a little bit. Fine, let's look at another control statement, and that is a break and a continue. And this is very interesting. If you put a break inside of a block, and that block happens, for instance, to be a for loop. If it sees a block, if it sees a break, then it will actually stop and drop out of that loop, out of that block, and carry on after the block. Okay? So if we break, the command is immediately drop out of executing this block that you're currently in. Okay? However, if we put a continue inside a block, then it says, okay, stop executing this time through the block, but this time around, but carry on. If there are any other iterations, you can carry on from the beginning. In other words, only stop doing this iteration. It's like break, but instead of dropping out all the way, it says just drop out of this iteration this time around and carry on and do the rest of them as normal. So let's have a look at that in an example. So we load up the program, the example, BrightSparks, break, continue. Okay. So now we're going to look at the break part of it. Normal, loop for int, I is naught, I is less than 10, I plus plus. Serial, print I. Okay. And print a space after it. Okay. Now, if I is equal to 5, then I must break. Okay, so I drop out of this loop, this for loop that I'm running through. I drop out of it, and there's nothing more to do. Okay, but if I don't break, then I carry on and say do some more and delay 100 so that it doesn't rush so much so fast. So here we upload it to our microcontroller. Have a look what's happening. Okay, now I'm going to stop the auto scroll and look at this. Okay, 0, do some more. 1, do some more. 2, do some more. 3, do some more. 4, do some more. 5, and there's no do some more. Why? Because when we got to 5, we actually braked. it saw break, which means it didn't carry on saying do some more. It didn't carry on saying do some more, and it jumped and dropped right out of that, and it starts all over again, right? I can even put a message here after everything's done, and I can say serial print line finished this loop through loop. Okay, semicolon, end of our command. So let's now see what that does. Upload to the microcontroller, have a look to see what's happening, switch back our auto scroll on. Okay, and let's see what's happening. The minute we hit 5, we print, we drop out, okay, drop all the way out to the end of this for loop. There's the start of the for loop, there's the end. So we drop out of there and drop out of the for loop, sorry, there's the for loop from there to there. We drop out of the for loop and we do the next thing in the list, which is just finish this loop through loop. And then we're the end of a loop here, and we go up and we start again. 0, 1, 2, 3, 4, 5, up, we equal to 5, break, and fall out of the rest of the loop. Okay, now let's load BrightSparks 1.1 break, continue, 1.1a, continue. Now let's see what's happening here. Still everything's the same, but we say if I equals 5, continue. Okay, now it's not break. The only change there is break. And maybe I'll put here that message to say we finished the loop. Okay, so finished the for loop. So let's try loading it, uploading it, and have a look to see what's happening. Okay, I'm going to switch on auto scroll, and now what do you see? Switch it off again so we can see what's happening. Okay, 0, do some more. 1, do some more. 2, do some more. 3, do some more. 4, do some more. 5. It's now seen 5. And what has happened? It has continued. So it skipped over the rest of this and jumped to the end of the for loop. But then it carries on with the for loop. So carries on, and then I is 6, 7, 8, 9. And then we finish the for loop, finished. And then we do some more, and so forth. Right? So continue, break, we drop all the way out of the for loop, all the way to the end. Continue, we just skip the last commands inside of this for loop, this specific loop, and carry on with our for loop. Right, interesting, isn't it? And in that way we can get things exactly the way we like them. Fine. What about our next command, that flow control command, and this is do while. Okay, so we actually have two here, which I'm going to mention both before we actually go to our programming. And the do loop just starts with do, braces, and here's what we're going to do over and over and over again. But when we reach the end, we ask, is this true? If this is true, then go and do it again. Okay? If this is true, then go and do it again, and so forth. Right? So that is our do loop. And then we can flip it around, because here we're going to do the do loop at least once. Okay? There's no questions being asked before we enter here. So we are going to do this do loop at least once. What if we don't want to do it at least once? Well, then we just flip it around and put the while at the top, no do at the bottom. And we say, while this is true, do this. While that is true, do this. While that is true, do this until you fall out the bottom, because that is no longer true. Okay? Fine. So let's go to our IDE. And I'm going to close my serial monitor and load up BrightSparks do while. Okay, that's the first option, our do while option. Okay, so the rest of this is the same. We just start with some other integer, I, equals 0, and we say print with a line, feed with a new line, I equals I plus 1. Okay, so we're doing that inside the loop. That's what we do inside the loop. And then at the bottom, while I is less than 10, carry on doing the loop. Fine. So we'll go around, go around, go around, go around, go around. When I is 10, we fall out the bottom. Okay? But that's the end of the loop. So we go to the top again, and it says I equals 0, and we do it again. Okay? So let's try that out. Upload. Look at the serial results and switch off the scrolling. Okay, so we start with I is 0. There's I equals 0. We start with I is 0. Do serial print 1, 2, 3, 4, 5, 6, 7, 8, 9. When it's past 9, it then starts with 0 again. Okay? Now, what if, and this is just some interesting stuff, interesting aside, let's now look at our next option, and that is, IDE, load the example, just while. Okay, and now we have I equals 0, initializing it, while I is less than 10, print I and a line, new line, I is I plus 1, and carry on. So here we're going to carry on. We're not going to go in a for loop, we're just going to go until I is 10, then we're going to drop out and go back to the beginning again when I is 0. And incidentally, just so that we understand each other, what we had there is completely analogous to that. Okay? So int I and setting it to be 0. So that is just a shorthand for this. What we have there is just a shorthand for that. Okay, so we're going to print, but notice I'm not putting the delay in. So I expect the computer to give up again and break the serial connection. Let's just try. I honestly haven't tried this before, so I'm now going to be as interested as you are. Upload and look at the results. Okay, it is going at one massive rate, and let's close that. Excuse me, and now try uploading again. No, it has managed this time, but whatever. When you are printing out very fast, give yourself a little delay in between, just to allow the computer to catch up. Obviously, a normal program will have a lot of stuff inside here, inside the loop, and so you don't have to delay anything. The program itself will delay enough. Upload. And look at the output. Okay, we're going slowly because we have the delay inside there. Right, and that concludes this lecture.